Hello there, this is Ms. Page. In this lesson, we are going to talk about how to graph some simple logarithmic functions by hand. So we're going to look at one way that we can graph a logarithmic function. So we can so let's say we want to graph, for example, a logarithm that is base 2, which will be one of the ones we focus on. Then we can start with the points that represent the powers of 2. These would actually be the same points that we use to graph the exponential functions with a base of 2. The difference is because the logarithm function will be the inverse of the exponential function, we will take those original points and we will switch the x and the y for that inverse relationship. So then that means that our x's will become the values of the power, like the powers of 2, and the y's will become the exponent values, which we used from -2 to +3, I believe. So those will flip-flop, the x's and the y's. And then we will graph those points and apply the transformations that are in the logarithm function. So base 2, so some people who are really good with just kind of remembering key points for all different types of functions, you can graph them directly using the key points of a logarithm function as the parent. So this is our base 2 logarithm function shown here. And it has an asymptote that is the y-axis, a vertical asymptote of the y-axis. And we're looking at some of the key points here that we would graph, which are the powers of 2 where the x's and y's have been switched. So this is what I was referring to. So our y is now our exponent value. Here the one for -2 isn't shown, which gave a power of 1/4, if you recall. So these are from -2, or -1 rather, to +3. Those are your exponents. And then your x's are now your powers of 2. So 2 to the -1st is 1/2. 2 to the 0 power is 1. 2 to the 1st power is 2. 2 squared is 4. And 2 to that exponent of 3 gives us 8. So they flip-flop because of the inverse relationship. So if you can remember, what they are in their logarithm form, then you don't have to do the switching. Personally, I just prefer to remember fewer points. So I just remember, okay, let's do my powers of 2, switch them, and then I can transform them. Base 10 logarithm, same thing. Here we see our base 10, which is our parent for our base 10 logarithms. Also has a vertical asymptote of the y-axis. And here are some of the key points. The 100,2, very rarely are we going to see that on a graph that we do by hand. So generally speaking, we will use, say, these 3 as our key points. Then we have our base e logarithm, which is our natural logarithm. This is our parent function, ln of x. And so the powers of e we'll use are the same powers of e that we used for our base e exponential functions. Also, notice vertical asymptote for the parent function is the y-asymptote. That is consistent with all of the parents. So the vertical asymptote always starts at the y-axis and then it moves left or right depending on the horizontal translation, which is created from h. So here we're looking at the structure of our logarithm functions that we will be graphing by hand. Notice inside the parentheses, which is our argument, in order for us to correctly identify any reflection across the y-axis, horizontal stretch, horizontal compression, that the coefficient of x, if it's something other than +1, needs to be factored out, or we won't get the correct h value to tell us what our horizontal translation is. So we want to be careful about that. Vertical asymptote, which will shift from the y-axis left or right, depending on the h value, has an equation then of x equals h. For these simple ones, our domain, well, we don't will end up usually being x is greater than or less than that h value for where our translation left or right happens to be. And remember that the range for our logarithm functions is the set of all real numbers, but if we're doing it in our set notation with inequalities, you want to make sure that for range you do use a y value. All right, so we're going to graph and we're going to do some key features here. So here we're going to graph g of x, which is, we have to recognize a logarithm of base 10 because we don't see the subscript base. So a couple of things I would do here. I would identify the transformations based on my parameters, and I would write down my powers of 10 points. So my powers of 10 start off as -1, 1/10, and these are from 10 to the x. These are the exponentials. 0, 1, and then 1, 10. Using my inverse relationship to get my logarithm of base 10, then what I'm looking at is 1/10, -1, 1, 0, 10, 1. My transformations that I'm going to perform on my logarithm key points there. So I have a -3 as my a value, which means that we have an x-axis reflection and a vertical stretch by a factor of 3. And then our +2, which is not inside parentheses, would be identified as the k value. So there is a translation up 2 units. Our h value here, since there is nothing inside parentheses that is added or subtracted from the x, our h is 0. And that tells us that our vertical asymptote, y equals 0, or x equals 0 rather, the y-axis, is not going to move this time. It's going to stay exactly where it is. So this allows us to do our asymptote, which will be x equals 0, our y-axis. All right, domain. We could identify the domain based on what we've learned about doing domain algebraically, or we could wait until the end of the graph and do it from the graph, which is what I'm going to do here. Range you can do right now. It's got 2 blanks because we're going to do it both in our set notation and in our inequality notation. Range, remember, is about y, so for your set it's the set of all y's such that, and the range of our logarithm functions is always the set of all real numbers. So we have -infinity is less than y, and y is less than infinity. And then our interval notation, like so. So we can do that. We can do our asymptote, 0. Y-intercept is something that we're going to wait and probably perhaps have to estimate. We could actually do the y-intercept, mathematically speaking, because our x would be a 0, but what we would get, without a calculator, it's a little harder to do, and we're not going to bother with that right now. And then end behavior, we'll wait until the end of the graph, and whether we have an increasing or decreasing function, we'll circle which one we have there after we've done the graph. Not that you couldn't figure those things out, but when you first start this, it will definitely be a little bit easier until you get used to the logarithm functions and what they look like to start with and how they'll transform to the end product. That takes a while to get comfortable with. All right, so let's go ahead and draw our axes. So my x-axis reflection is going to take my logarithm function, which starts as an increasing function, and switch it to decreasing. But unless I have a y-axis reflection, my points are still going to be to the right of my asymptote. So notice how in all of our parent logarithm functions, all of these graphs, all of our curve is to the right of the asymptote of the y-axis. The only thing that would change that is if we have a y-axis reflection, which would flip it over to the left side of that asymptote. So that tells me that all of my points are going to be still on the right side of my asymptote, which remember is remaining the y-axis. So I'm going to put my y-axis maybe over here or even on the edge if you prefer. And then my x-axis. So I do have a shift up 2. So all of my y values will move up 2. So the y value of 1 here in this third point is going to move up to 3. Other than that, it's not a big deal. So I'll move my x-axis down maybe a little bit, but it's not going to be that, well, actually I do have a reflection. No, it'll be the same, because our negative one will reflect to 1 and then go up 2. So, oh, we have a stretch. Forgot about my stretch. All right. If I do have a stretch of 3, then the 1 does stretch to 3 and then also reflects. So, and then goes up 2. So I think I need to get to 5. So 2, 4, well, that probably would still work. Okay. So all those things to think about. So it is very possible that when you're graphing one of these, especially if there is a stretch, that maybe you do have to move that x-axis to graph all the key points onto the grid that you've got. Let's put some numbers on here to help with graphing things accurately. All right. So now I'm going to start transforming. I like to start with 10(1) myself because just don't have to worry about the fractions and the negatives at the beginning. So 10(1). So remember that you have to do all of your A transformations first. It does not matter if you do the reflection or the stretch first, but you do have to do them before you do the up to translation. So I'm going to stretch to 3, and then that will reflect down to -3, and then it will move up to 2. Like so. My 1, 0, which starts here on my x-axis, the stretch and the reflection don't affect it because it's like multiplying times 0. And but it does move up 2. So now it's here. And then I have this 1/10, -1. So -1 times 3 is -3. So there's my stretch. And then it reflects, so it becomes a +3, and then it moves up 2 to 5. Now remember, your asymptote is your y-axis. So I'm going to put a dashed line there, but on graphs by hand, if that asymptote is the axis, you don't have to do that, but I would encourage you for your notes to do that. And then I'm going to draw in my curve, so I can tell here that the way my points are curving, that my left end is going to be heading towards the asymptote. And then it curves down and comes through like so, and it keeps heading downwards as x gets larger. And so there's a simple graph of g of x. All right, so now to do our domain. So our domain is our x values, and so we can see that the x's that go with our points are all to the right, which would be greater than our asymptote x value, which is 0. So this would be the set of all x's such that x is greater than 0, and that would be from 0 to infinity, non-inclusive. For the 0, we're going to be estimating this. So some of you, your 0 might look different on your graph because, you know, there was quite a gap between these 2 points at 1, 2 and 10, -1. So my 0 ends up right about there, which is about 5.2, I would say. Yours might be in a slightly different place, and I'm fine with that. Just estimate it based on how you curved the function. So I'm going to say my 0 is about 5.2. You might have to have a slightly different number. Y-intercept. So here, because our asymptote is the y-axis, there will be no crossing of the y-axis. So there cannot be a y-intercept. So here we will say none. end behavior. So our left end, this is where normally x goes to negative infinity, but because of the asymptote, the vertical asymptote, it can't do that. So the left end, x can only go towards the x value of the asymptote. So x is going towards 0 on that left end. And then our function g of x values, that's the arrow heading up for y, so that's heading to positive infinity. The right end, which is where x goes to positive infinity, it's still going to do that because it's not stopped by an asymptote on the right. So we have as x goes to positive infinity, our function values are heading down, so the y's are going to negative infinity. Increasing versus decreasing function. So remember, that's a left to right. So looking at our curve from left to right, it's heading down. So this time this function is decreasing, like so. And that finishes up everything here. All right, let's take a look at this example. So here we're going to graph a natural logarithm function. Natural logarithm functions, remember, are base e logarithms. So the points that I would look at would be those powers of e, from e to the x. So if I've got 0, e to the 0 power is 1. If I have x is 1, e to the first power is e, which is about 2.7. If x is 2, e squared, remember, was about 7.4. Now what I want is my natural logarithm, which is my log base e. So we flip them because these are inverses. So this becomes 1, 0, 2.7, comma 1, 7.4, comma 2. So these are my key points here that I'm going to transform. So looking at my parameters, my a value here is 0.5. So that is going to give me a vertical compression by a factor of 1/2. And then notice how this time the plus 2 is inside the parentheses, so the 2 is added to the x. That means I'm dealing with an h. So remember, you have to take the opposite of that to get the correct h value. So our h value is -2, which means we have a translation to the left 2 units. That is going to move our vertical asymptote from the y-axis to x equals -2. Like so. Range, remember, of all of these simple logarithm functions is the set of all real numbers. So we have the set of all y's such that negative infinity is less than y is less than infinity. Everything else, once again, I will wait until after I do the graph. So now I'm going to draw in my axes. So for my y-axis, I need to be able to graph my dashed line for my asymptote at x equals -2. And so I'm going to move my y-axis, say, here. And that will allow me then to put my asymptote over there at -2. All right, compressions, generally then that means we're not going to have to worry too much about the position of our y-axis. And we're not moving up or down this time, so that's not a big deal. So I'm just going to put my x-axis in the middle here. All right, let's put some numbers on here to help with the graphing. And let's graph our dashed line for our asymptote at x equals -2. So this time it is required that we graph this dashed line. Okay, so now I'm going to start transforming my natural logarithm key points here. I'm going to start with 7.4, 2. So here's 7, 7.4 is not quite halfway, comma 2. So I'd have to do the compression first. So I'm compressing this vertical distance of 2 by a half. So it's like 2 divided by 2, which is 1. So it compresses to here, and then it moves left 2, 1, 2, and ends up right about there. Then I have this 2.7, comma 1, which is my E, comma 1. And so 1 compresses by a half unit. So 1 divided by 2 is a half. So I'm now here, and then translates left 2, 1, 2. Ends up in the middle of that square, right around there. Then I have my 1, 0, which is here on the x-axis. The compression doesn't change it because I'm multiplying or dividing 0 by 2, or multiplying 0 by a half, so it's still 0. But it does move left 2. 1, 2, and ends up right here. So this time, my lower point, my leftmost point is lower, so that means that my left end is heading down towards my asymptote, like so, curving up through these other points, and it's going to continue upwards like so. There's our graph. So our domain here is going to be the x values to the right of our asymptote x of negative 2. So we've got the set of all x's such that x is greater than negative 2. Interval would be from negative 2 to infinity, non-inclusive. 0. This time I have a very nice 0 that everybody should have the same answer for. It's right there at negative 1. This time I have a y-intercept, which, well, my y-intercept might be a little different from yours, but they should all be fairly close to one another because these 2 points were so close. So my y-intercept is right about here, which doesn't look like it's quite to the halfway mark. So I'm going to say it's about 0.4. So 0, comma, actually let's put my approximate in there. I like that better, like so. All right, so now end behavior. So my left end is heading down to my asymptote. So my x, again, as I head to the left, I can't go all the way to negative infinity because of the asymptote. So the x on that end is heading towards the x of the asymptote, which is negative 2. And then the y's, or g of x function values, are heading down, so they're going to negative infinity. The right end, x is going to keep going all the way to positive infinity. And this end is also heading up, so our y values are getting larger and going to positive infinity. Increasing versus decreasing, well, left to right, our function is heading up, so this time we get an increasing function, like so. All right, all done. Okay, let's take a look at this one. So this time we're going to graph a base 2 logarithm. So that means that for our key points that I would want to be looking at, I would use my powers of 2, my 2 to the x. So the ones like on the graph started with an x of negative 1, so I'll do that. So negative 1 would give me 1/2, 0 would give me 1, 2 to the first power would give me 2, 2 squared would give me 4, 2 to the third power would give me 8. So now I'm going to flip those to get my log base 2. So this is going to become 1/2 negative 1, 1, comma 0, 2, comma 1, 4, comma 2, 8, comma 3. So these will be the key points I'll transform. So now I have to figure out what my transformations are. So my a value is 1, so nothing going on there. My k value is 0, so nothing going on there. But notice this guy in here. This one is a little tricky if you're not careful. 4 minus x is the same thing as negative x plus 4. So our coefficient of x is a negative 1. And remember, that's not going to help us get the correct h value. So if we factor out that negative 1, then what we really have is x minus 4 in parentheses. So it's the opposite of negative 4, that's our h. So our h is positive 4, which means that we have a translation to the right 4 units. The negative 1, remember, that's our 1 over b, which in these notes is called a c. But that is the parameter that handles the y-axis reflection when it's negative, like here, and then stretches and compressions in the horizontal direction. So the absolute value is 1, so no stretch or compression horizontally. But the fact that it's negative tells us that, I'm going to call it C like in the notes, it does tell us that we have a y-axis reflection. Now this is important because that means all of our points are going to flip to the left side of our asymptote. And our asymptote is moving from the y-axis over to x equals 4. Range, still the same, always, set of all real numbers for these simple ones. So the set of all y's such that negative infinity is less than y is less than infinity. Everything else will wait until the end to complete. So now I'm going to draw those asymptotes, or sorry, axes. And so I have to make sure that my y-axis is positioned so I can still draw my asymptote at x equals 4. And I don't want it to be completely on the end, I don't think. So I am going to make this 4, 3, 2, 1. That would put my y-axis here. My y values, as you can see in my key points, only go up to 3, and so they're not going to be vertically stretched or anything like that, so that's not a big deal. So I'm just going to put my x-axis in the middle here. Let's put some numbers on this to help with accuracy. All right, so now let's start transforming points. So I'm going to start with 8, 3. So what 8, 3, remember you have to do your y-axis reflection first, then move right 4. Oops, my asymptote. Let's put that in there. Dash line for my asymptote. I'm going to want that. It's going to help me visually know I'm doing my points right. So 8, 3. So 8, 3, if I do my y-axis reflection, it's the x that changes to negative 8. So it flips over here to negative 8, 3, and then it moves back to the right 4. 1, 2, 3, 4. Ends up there. Then my 4, 2, flip it to negative 4, 2, move it to the right 4. 1, 2, 3, 4. 2, 1 flips to negative 2, 1. Count 4 to the right. 1, 2, 3, 4. 1, 0, which is here, flips to negative 1, 0, and then moves right 4. 1, 2, 3, 4. And this 1/2 negative 1 flips to negative 1/2 negative 1, and then moves right 4. 1, 2, 3, 4. So our curve on the right end this time is heading down towards our asymptote, and then it's curving up to the left through the other points like so. All right, so now let's look at our domain. So here we can see that our domain would be x's to the left of 4, which means they're smaller or less than 4. So our domain would be the set of all x's such that x is less than 4. In interval notation, remember, that would go least to greatest, so that would be negative infinity to 4. Now I'm looking at my 0. So this time again, everybody should get the same value for the 0 because we have a nice 0 right there at positive 3. And this time everybody should get the nice same value for the y-intercept because that's one of our key points also. So that would be 0, 2. Now end behavior. So your left end this time is going to be able to go all the way to negative infinity for x because there's no asymptote on the left side to stop it this time. So this time our left, x goes all the way to negative infinity. Our function or y values, the function is heading up, so we're heading to positive infinity for y. This time on the right end, though, x cannot go all the way to positive infinity because the asymptote will stop it. So our x's are going to that x value of the asymptote on this right end. So on the right, as x goes to positive 4, our function values are heading down, so g of x is heading to negative infinity. All right, and then increasing versus decreasing is still done from left to right. So starting over here on the left and following my curve, it's heading down. So this one is a decreasing function. And that finishes this one up. All right, so those three examples, one of each type of logarithm that we're graphing, base 10, base e, the natural logarithm, ln, and the base 2. So now we've got some practice problems, so I encourage you to pause the video, do the problem, come back to check your answers in your graph when you are ready. Let's take a look at this one. So you can do a comparison here with your answer and mine. Let's take a look at another practice. So pause the video here. All right, we're going to take a look at this result now. Again, you can do a comparison between what's here and what you have. See if everything matches. So now we're going to look at closure. And closure here is important. We're looking at here, will a logarithmic function always, sometimes, or never have a y-intercept, and be able to explain your conclusion. So we looked at this type of thing for exponential functions also, y-intercepts and zeros, and what we knew about them for exponential functions. Here we're doing the same for our logarithmic function. Notice it doesn't say what base. So this is about all of those simple logarithmic functions that we've been graphing by hand. So will a logarithmic function always, sometimes, or never have a y-intercept? So if we look back, we have some good examples that show us that the answer here will be sometimes, because the value of 0 is sometimes part of our domain. So it depends on where our vertical asymptote is. And so if 0 is part of the domain, then we'll have a y-intercept. If 0 is not part of the domain, then we will not have a y-intercept. So there is sometimes a y-intercept for these logarithm functions. Now we want to be able to also understand, will a logarithmic function always, sometimes, or never have a 0, and be able to explain our reasoning there. So zeros, remember, are those intersections with the x-axis, those x values. So thinking about that, well, what do we know about the range of logarithm functions? So remember how the range of our logarithm functions is the set of all real numbers? So if the range, if the y's go from negative infinity to positive infinity, then a logarithm function is always going to intersect the x-axis, which means that you're always going to have a 0. So you always have a 0 for a logarithm function, but you sometimes have a y-intercept because in a logarithm function, the domain is restricted. And this, if you recall, is the reverse or flip of our exponentials. In our exponentials, our domain was the set of all real numbers. That's now our range for the inverse functions, our logarithms. And in exponential functions, we had a range that was restricted. So that switches now to the domain being restricted for the inverse logarithm functions. And so that helps us better understand y-intercepts and zeros for these types of functions. All right, that finishes up this lesson. I hope you have a lovely, lovely day. Bye-bye.